Alright, silly people, here's the situation. We're going to be looking at the scattering states for a particle that is going through this potential, which is like the rectangular potential, but it's positive rather than negative. Um, and we're going to be looking at it in various cases, which I'm going to talk about in a second. But first of all, let me write out what the wave functions on either side of the potential are. Let me or let me label the sides of the graph. Actually, this is going to be region 1, region 2, and region 3 for future reference. And so, much like in the book, the region uh, 1 wave function is a e to the I kx plus b e to the minus I kx. And then the region on the right of the potential, so psi 3 is going to be f e to the I kx, assuming scattering from the left. Um, so that's all cool. Um, and then we have this new Schrodinger equation, which we haven't dealt with before, really, um, which is del squared psi 2 del x squared plus v naught psi 2 equals e psi 2. And then standard procedure is to put the derivative on one side of the equation, then everything else on the other. So we'll have 2m over h bar squared, and then this is going to be v naught minus e acting on psi 2. And then you collect it into a term, which I'm going to call L, and this is going to be L is going to be defined as root 2m v naught minus e square root of all that junk divided by h bar thing. Cool. And so now the differential equation will look kind of solvable. In fact, it's very solvable. But depending on the relationship between V naught and E, you're going to get different solutions. So, first of all, let's do this all in black actually. For E less than V naught, this is the first case that Griffiths asks us to look at. So, that is just saying that L is positive and real, right? Because V is positive and E is not as big as V, so yeah, positive and real. That has a particular solution of c e to the lx plus d e to the minus lx. And the goal of this is to find the transmission coefficient. So we're going to play around with a bunch of boundary conditions involving psi 1, psi 3, and psi 2. The first one I want to look at is actually the continuity at A. So psi 2 of A equals psi 3 of A. And that's going to give us c e to the LA plus d e to the minus LA equals f e to the IKA. That's very cool. We're going to use it to solve for C, and say that C is going to be f e to the IKA minus LA minus d e to the minus 2LA, right? Next boundary condition, psi 2, or the partial derivative of psi 2 with respect to x at A is equal to the derivative of psi 3 of x at A, right, the smoothly varying condition. So we have LC e to the LA minus LD e to the minus LA equals F, nope, IK F e to the IKA, right? Um, and then we just solved for C, so let's plug that in. So we have L times F e to the IKA um, minus LD e to the minus LA, and then this term from before, and then this junk. Right. Okay. Um, so we can combine the terms which depend on D and put them on the left side. So we'll have 2LD e to the minus LA, whoops, minus LA. And on the right side, we'll have just F e to the IKA stuff. And let me actually write properly. And then that's just IK minus L, right? And then use that to solve for D. So we have D is equal to F e to the IKA plus LA, and then we'll have dividing by 2L or minus 2L, we're going to have 1 half minus IK over 2L. That's kind of gross, but we are going to take it to the bank with us. So this is going to be important later. Now let's take what we got for C from before and plug D into there for completeness. We have C equals F e to the IKA minus LA, and then minus F e to the IKA, again minus LA, but then also with this 1 half minus IK over 2L, right? So we'll just collect those terms. We'll have F e to the IKA minus LA. This is going to be 1 minus 1 half plus IK over 2L. So it's, you just subtract a half from 1. You get 1 half plus IK over 2L for C. And we'll also take that to the bank with us. Right. Now we have to deal with the other two boundary conditions. So that's going to be that the wave function will be continuous at minus A. So we have A e to the minus IKA plus B e to the IKA equals C e to the minus LA plus D e to the LA. And we're going to use this to solve for B. So just looking at that, we're going to have B equals C e to the minus LA minus IKA plus D e to the LA minus IKA, right, minus A e to the minus 2 IKA. Okay, that's interesting. Then the final boundary condition from which we will derive the transmission coefficient will be this, that the wave functions are smoothly varying at x equals minus a. Right, so we just got ik e to the minus ika minus ik e to the positive ika, and there's a b there, and then equals the lc e to the minus la plus minus ld e to the la. Cool. First of all, let's plug in what we just got for b. So ika e minus ika, and then we got minus ik c e to the minus la minus ikd e to the positive la minus or plus ika e to the minus ika, right? And then on the left side, hand side, we haven't changed anything yet. Okay. Then we just group up these a terms over here, e to the minus ika, and on the right hand side we'll group together the c and d terms, which are going to be just c l plus ik, and then this is going to be e to the minus la, of course, plus d, and then it's going to be minus l plus ik. Yeah, they're both plus ik. That's interesting. Ik minus L then. Alright, and that's e to the positive LA. Now we plug in what we boxed before for C and D on the right hand side. So C was that, so we have F e to the ika minus 2la L plus ik times 1/2 plus ik over 2L, right? And then the D term had a similar looking thing. It's now F e to the ika plus 2LA, and then times the term which comes from the other boundary conditions, and then that last term times the ik minus L thing, which we just got. Yeah, the equation's already getting a little bloated. So let's go ahead and let's actually go ahead and divide everything by 2ik. So a e to the minus ika on this side. The right side will have f e to the ika, and then we're just going to group all those terms together because they both depend on f e to the ika. But then here we'll have L over 2ika, which is the same as minus IL over 2k, plus ik over 2ika, which is 1/2 e to the minus 2la, and then this is plus, we'll have another couple of terms. Ik over 2ik is 1/2, and then minus L becomes positive IL over 2k into 2LA. But I've been neglecting some terms actually, because there is this term here, which is 1/2 plus ik over 2L. And then there's also this other term which comes from this equation, 1/2 minus ik over 2L. And then let me see if I can squeeze the last bit onto there. I can't, of course I can't. We're just gonna say times that. Right. Uh, we are going to have to expand both of those um, multiplied polynomials by each other. So let's just get on with that. Without changing the left-hand side at all, this is going to get pretty big because we're going to have expanding the first term, which depends on e to the minus 2LA. We'll have ik over 4L by multiplying this term with this term. And then we'll also have a minus I squared KL over 4KL, multiplying this term with this term. And then multiplying this term with this term, you just have a fourth. And then finally this term with this term, you have minus IL over 4K, right? Yeah. Yay, e to the 2LA. And then there's also a plus all the other stuff. So this term minus times this term makes a fourth. This term times this term makes plus IL over 4K. This term minus this term makes minus IK over 4L. And then this term times this term makes minus I squared KL over 4KL. All times e to 2LA. And so I squared is obviously minus 1. So we'll simplify that a bit. We'll have ik over 4L, and then it's minus, so positive 1/4 plus 1/4, so plus a half. And this is minus IL over 4K into the minus 2LA. And then in here, we still have the 1/4, but again, that's 1/4 as well. So it's 1/2, but now plus IL over 4K minus IK over 4L. And my handwriting is already getting bad. And that's e to the 2LA. Okay. There's a better way to group this, as there often is, because there's a 1/2, and then the 1/2s share the signs within the parentheses. They're both positive. So this is e to the 2LA plus e to the minus 2LA. And that just looks like a trig function waiting to happen. But then there's also this IL over 4K minus IK over 4L, which change signs in between. So there's an e to the 2LA minus e to the minus 2LA, right? Again, like a trig function waiting to happen. So we're going to look at these like it's hyperbolic cosine or cosh of z equals e to the z plus e to the minus z over 2. And then hyperbolic sine, which is sinh. And then we get the z e to the z minus e to the minus z over 2. So that's how we're going to get the form that Griffiths got. We were going into hyperbolic stuff. So now we got cosh z plus, and then we have I here, but then these things have to be multiplied by 2, so it's going to be IL, nope, it's just going to be now L over 2K minus K over 2L, and that's multiplied by sinh of Z. And I don't know why I'm writing Z. It's actually 2LA. 2LA, right? Nice. Uh, and remember this all of this is equal to a e to the I k a or minus I k. It doesn't matter because what we're going to do now is we're going to say take the square modulus of both sides. So we'll have a square modulus of f on the left. And then the nice thing about how we grouped it together just now is that because now this is just a real plus an imaginary, take the complex conjugate, or take the square modulus anyway, and then the cross terms will cancel each other out. But then we'll still have the squared terms of either side. So plus L over 2k minus k over 2L all squared, sinh squared, 2LA. On the right hand side it's just mod squared A. And so we can use this to solve for mod squared A over mod squared F, which by the way is just the inverse transmission coefficient. And then use one more trig identity that I probably already should have written. That is cos squared z minus sinh squared z equals 1. And so we can turn that hyperbolic cosine into a hyperbolic tangent and just be like 1 plus sinh squared z. But then we have the sinh squared term with a polynomial, which I'm going to go ahead and expand because we'll have a L squared over 4k squared minus k squared over plus k squared over 4L squared minus, and it's just going to be minus a half. Sure. Yeah, minus a half. And that's multiplied by sinh squared 2LA. Right? So, and again, I'm doing this thing where I shouldn't be writing z like a fool. It's late. We're going to move that positive sinh squared of 2LA into this term, which involves them as well, for simplification purposes. So now we're going to have L squared over 4k squared plus k squared over 4L squared plus a half, right? And so what we do is we make it so that all of these terms have the same denominator. So this is going to be multiplied by another 2 factors of L, so L fourth. That's going to be k fourth, and that's going to be 2k squared L squared. That's going to be all divided by 4k squared L squared. Right. And so rather than plugging in what L and K in are right now, it's worth observing that the top line of that fraction is literally the same as L squared plus K squared all squared. And that is going to save us some pretty rigorous calculations, excuse me. I'm disgusting. Okay. We're going to now expand L and K. And I'm pretty sure I wrote L up there before, but I'll write it again because it is actually L equals root 2m v naught minus e all over h bar. And then K that I've been referring to. I'm pretty sure it's K. It might be kappa in Griffiths' notes. It's in the section preceding this problem, but it is just square root 2me over h bar, right? Uh, and so those are pretty easy to square and do things to. So all squared plus k squared all squared looks like 2m v naught minus e over h bar squared plus 2m just e over h bar squared all squared, and then the inverse 4k squared l squared thing. So this is going to be 4 times h bar squared over 2m v naught minus e, and then this is already getting out of hand. The 4 should be down here. That's the joke. Yep. Okay. 4 2m v naught minus e, and then another h bar squared, and that's going to be over just 2me, right? And that's all of that is multiplied by sinh squared 2la. Okay. So in the parentheses, this is just turning into 2m v naught over h bar squared, because the e terms actually cancel out in there. That's why it was so nice to do that. Up top we'll have an h bar to the 4th. On bottom we'll have a 16 m squared e, and it's v naught minus e, not the other way around. And then sinh squared 2la, and then we can square the stuff into parentheses to have 4m squared v naught squared over h bar 4th. And hey, the h bar 4ths and the m squareds are going to cancel out a little bit. So it looks like our final expression is going to be 1 plus v naught squared, and then the m squareds go away, the 4 on top, 16 on bottom just turns into a 4 on bottom, e v naught minus e, and then sinh squared, and at this point it's worth plugging in actually the definition of L into the sinh function, so we have root 2m v naught minus e. And all of that makes the result that Griffiths got, so we are good there. The next case that Griffiths wanted us to check is if v naught is equal to e, and that's a pretty funny little situation to check, because again, L is defined the way that it is. So if E is equal to V naught, L is 0, because they're canceling each other out, which means let's do the rest of this in blue. For E equals V naught, we have that L equals 0, and the Schrodinger equation is the simplest kind of differential equation you can ever have, with 0 on the right hand side. So we can quickly solve that just by integrating it a couple times. You get a constant c times x plus d. Pretty cool stuff. We are going to do our boundary conditions same way that we did before. We just have psi 2 of a equals psi 3 of a. And then we have, so that's CA plus D equals, on the right hand side, it's still F e to the I K A. We're going to use this to solve for C, so we'll say C equals F e to the I K A all over A minus D over A. Pretty cool stuff. The next boundary condition we can do is that the wave functions are smoothly varying at A. So del psi del x at A. So we have just C on the left hand side, on the right hand side it's I K F e to the I K A. And then we can just plug in what we got for C, so F e to the I K A over A minus D over A equals I K F e to the I K A, and then we can use this to solve for D. So from this, it looks like D equals F e to the I K A times 1 minus I K A, just doing a bit of algebra there. Rather than now plugging in what we got for D into our expression for C, we're actually going to take this equation to the bank, because that's as best as we can get already. Anything else would be superfluous. Finally, we can check psi 1 at minus A equals psi 2 at minus A. So we'll have just A e to the minus I K A plus B e to the positive I K A equals D minus C A, and we'll use this to solve for B. So we'll have B equals D e to the minus I K A minus C A e to the minus I K A minus A e to the minus 2 I K A, and then we'll check the smoothly varying boundary condition at minus A. Del x at minus A. So we got I K A e to the minus I K A plus, or now this is minus I K B e to the positive I K A. On the right hand side, it's just C again. Fun. We'll just plug in what we just got for B. So minus I K D minus, or positive I K C plus I K A e to the minus I K A equals C, and then we'll just put 2 I K A e to the minus I K A on this side, and then C times 1 minus I K plus D times just minus IK. So this is actually plus IKD. Alright, now let's plug stuff in. For both of these, we have IKF e to the IKA times 1 minus IK plus IKF e to the IKA 1 minus IKA. And I feel like there was something I missed. I know what it was. It was an A here. So there's an A here. So there's an A here. Awesome. Now we're looking cool. The IKs do cancel out, so that's funky. So we have 2A e to the minus IKA equals just 2F e to the ika 1 minus ika. That's good. The 2's also cancel out. We'll take the mod squared of both sides. And so this is going to be just 1 plus k squared a squared. And much like before, we'll just solve for the inverse transmission coefficient, because that's something that Griffiths likes to do, which is going to be 1 plus k squared plus 1 plus k squared a squared. And using the definition of k from before, it's 1 plus 2m e a squared over h bar squared. Okay. The last case that Griffiths asks us to check is for the case where, for the case where E is greater than V naught, and this is essentially the same as the one that he did in the section preceding this chapter, because he was just doing the box potential but with V naught set to a negative number. But the condition was the same. E was greater than V naught in that case as well. So I'm just going to write down equation 2.172, which was his answer for this bit, but then just replace every V naught with a minus V naught to maintain the symmetry. And so you get a minus sign in the denominator there, and you get a minus sign there as well. And that should be it. Okay.